Thank you. Is this thing on? There we go. Well, thanks everyone for coming. As she mentioned, my name is Schrock. I'm the founder of, got a little feedback here. I'm the founder of Elemental, and kind of our purpose as a company right now is to host this open source project called Dagster. And I'm going to talk about what that is, basically show it to you through live demos, so let's hope that works. And also talk about it in relation to other technologies in this space, in particular Airflow, because that comes up over and over and over again. So we're going to talk about what its relation is to that technology. So what is this thing? We describe it as a Python library for building data applications. It's an open source project, but you might be asking, it's very understandable, what on God's earth is a data application? Why did you make up a new word? So, there's all this existing terminology in this industry. There's ETL, which is extract, transform, load. Then there's the dramatic reversal of ELT. It's this whole new thing where you swap the T and the L. And there's ML pipelines. And, we really think that a lot of this terminology doesn't really make sense anymore. So let's talk about ETL in particular. Right? ETL is a historical term, and it comes from way back in the day in the 70s, where you had one database over here and one analytical store over here, and you had a single T in the middle, and you extracted from the transactional database, did one transformation process, usually once per week, say, and then loaded it into the data warehouse, right? You typically did this in this sort of like drag and drop, vertically integrated tool. And what's weird is that people still use this term, ETL, but it has no relation to what it previously used to mean, right? ETL now means effectively any computation which moves data from one place to another. And in a modern context, that means there's generally multiple computational runtimes involved, multiple stages of materialization, many, many data sources. Some of them are transactional databases. Some of them just might be web scraping. Some might be ingest from a SaaS app. It's just an incredibly complicated world. And this stuff is also generally more critical to the functioning of your generalized application. Right? Then let's talk about ML pipelines. So you hear this all the time, right? A data scientist will say, like, I spend 90% of my time doing data cleaning and 10% of my time doing my job. What they're really saying in some ways is that the bulk of every ML pipeline is an ETL process, right? Just the very last stage is usually like shuffling that data into a logistic regression or some other off-the-shelf algorithm. That's the reality of the world that we live in. And so we really think of these things as all these things are instances of what we call data applications. And you can build a cohesive framework that can address all of these use cases and more. So let's talk about what this leads to. So I think a lot of it's because of this hangover that there used to be ETL systems and a new thing came on ML, and kind of like different types of people worked on those different types of things. And because of that, there's different technology stacks, and there's an unnecessary siloing between data engineering and data science. So this is most frequently materialized in the real world as I'm a data scientist and I got a task, and I was given, like, my boss gave me a CSV file, and they're like, do ML, make us money, please. And then you go off and you work inside that Jupyter notebook and you build some graph, and you can show it to a decision maker and be like, look, we can do this. And then it's handed off to the data engineers whose responsibility is to productionize it. And they often build it in a completely different technology stack. And this siloing and this relationship between these personas is actually very unhealthy. And what you really want is more of a world that looks like this, where data scientists have skills and capabilities that data engineers don't have, and vice versa is also true, but you have more overlap so they can kind of exist within the same framework, right? And the only way that I know how to make this happen is to create new tooling and new abstractions in order to make that relationship more harmonious. So, data application. ML is an instance of it, ETL, ELT, and what we define these things as is just both of those types of classes of systems, or all of those, they are all graphs of functions, or functional computations as it says up there, that produce and consume data assets, right? The last step of an ETL process, typically a file or a partition in a data warehouse, something like that, and the last step of an ML process is a model, right? Everything else about it, very, very similar. And the thesis here is that the current tools that we use do not match the complexity of the problems that we face, right? And you kind of like feel this instinctually when you're scratching together one of these data infrastructure projects. It's just always ends up as this disorganized mess that's where testing isn't really the way it should be. I mean, everyone knows what I'm talking about here, and you can see it in the end product from the data teams. And so in particular, I'm going to talk about Airflow and why Airflow alone does not save us here. So I guess before I go into this whole shtick, how many people have heard of Airflow in the audience? Okay, great. How many people have used it? This is amazing. This is actually, I was making this slide deck last week, and I didn't even think until this morning. I was like, is this audience actually going to know what this system is? But, so we can actually talk about this. So, Airflow. Let me see here. So, Airflow has issues. I think I might have lost a slide there, but it's okay. So, one interesting story is the lineage of Airflow. So, Airflow was invented in 2012 at Airbnb. True? Kind of. Its lineage actually comes from a system at Facebook called Data Swarm, which was created in 2007. So that's 12 years ago now. It's actually a fairly old system, and it's very similar to that system that was created in that time period at Facebook. And you know, the thinking in the industry has evolved since then. And no less than Max, the inventor, Max Boschemann's the inventor of Airflow, or as I like to call him, Mr. Data Engineer 2012 to 2015. He's now moved on to greener pastures. He started a startup based on a technology called Superset, so he's no longer that directly involved in Airflow. But he wrote this really interesting article like a year ago about how we need to bring functional programming practices to the data engineering ecosystem. And, you know, I think that's totally right. So he talked about all sorts of interesting things in that article. He talked about how functional programming leads to better reproducibility, that by thinking as these partitions that are immutable data structures, you can kind of like model this stuff better. You model everything with idempotent computations, which means that you can kind of instigate the computation again and be confident that it's not going to destroy any information. And that it makes it easier to manage the concept of time in these systems, which I'm not going to dig into that, but it's a very complicated problem. And so, you know, I loved everything Max was saying here, and he was the inventor of Airflow. But then it got me thinking, is Airflow really functional? Is it really? And I would argue that it's actually not. You can use it in the service of implementing this functional data engineering, but it does not naturally guide you to do it. I call this falling into the pit of success, right? You can use Airflow to do this, but it's not the natural thing to do. So there's a few core reasons for this. So DAGs and tasks in Airflow, and we'll demonstrate this, are not parameterized. They are functions which have effectively no parameters, right? That makes it not a function, pretty much. They also don't encapsulate data flow in any sort of way. If you look at an Airflow task graph, there's no way to know what data is actually flowing through that system. It's completely, the tool is completely blind to what the actual nodes of computation are doing. And then there's no metadata about that. there's no type information, and so on and so forth. And then another issue here is that the system infrastructure is not pluggable, which means that it's actually very difficult to execute Airflow DAGs and tasks in isolation, meaning that they always have to touch a database, you have to have a local install on your machine running, it's difficult to spin that up ephemerally, et cetera, et cetera. It makes it difficult to test. And so because of these limitations, there's actually some consequences here. One is that Airflow DAGs and tasks are effectively untestable. Right? As I said, and I'll go over in a second, they're basically functions without parameters. And if your function doesn't have a parameter, you cannot test it. Right? You can only invoke it, and you'll only ever get one result back. So it's like designed not to be testable, which is kind of concerning. And then because of this, it's really only a tool that's effective for data engineering and not so much for data science. Right? Parameterizing computations is incredibly important for data science, because you want to do hyperparameter optimization, you want to train what your training parameters are, the data inputting, that's input changes, right? And whereas with data engineering, the only parameter that matters is time, meaning like you're processing a different partition every day. And that time is the only parameter that Airflow supports natively. And the other thing is that Airflow is not suited for the full developer lifecycle, meaning that you don't use it when you're doing local development typically. You don't test within that system. Only once you've crafted your computation and you want to embed it in a DAG in production does Airflow come in the picture. And we think there should be a system that does the full developer lifecycle. So, hence this slide. You want a framework that supports the full lifecycle of data applications. That means when you develop it, you want to be able to test it locally, test it in a CI/CD pipeline, do integration testing, then productionize it, then schedule it, right? And you want to have one system that can kind of capture that whole process. And so I'm going to demonstrate kind of through demos, see if this works, how Dagster, and also I'll be introducing some of the concepts along the way, how Dagster addresses each of these steps. So let's go to develop. So this is kind of hello world for Dagster here. So you pip install Dagster. It's just a Python program. And the core abstraction here is we call it a solid. Okay? And the solid is a node of computation that consumes and produces a data asset. Right? The body of the function can be anything, meaning that you can use any computational framework, whether that's Pandas, PySpark, or you can even remote out and execute a command in a data warehouse or invoke a Spark Scala job, whatever. And you define inputs and outputs. So here's like the first thing, read CSV. And then this is like classic computer science blinking lights demo. So I'm like doing like an add operation. But this takes in a data frame, produces another data frame. And then you string these together, and this is how you construct that DAG. So we have this function like DSL that actually like assembles these things together and creates a DAG. So the moment that you have your code in that format, you have tools at your disposal. So hop here. This is just a web app running locally on my machine, and it's loaded up this code. And now we have all this tooling here. So we load up this DAG. You have descriptions of what's going on, so you can like view this and actually see and have context about what's going on, right? Now, let's say I want to execute this thing. Now, these types here, one of the things we have to do, we actually have to parameterize this thing. So this is one of the most important concepts in this system, is that unlike Airflow, where you kind of, the DAG takes in the config and then you construct the DAG out of that, this separates the DAG from its parameters. So whenever we have a DAG that we want to execute, we have to have the parameters in order to execute it. So in this case, right, we need to give it the path that it's going to operate on in order to execute, right? Well, one of the things we have is because this is all strongly typed, we have this strongly typed configuration system in here. We can actually, we have this tooling at our disposal to actually create these config files. So you say, hey, I need to provide to this solid an input named path. And my personal lineage at Facebook was creating a technology called GraphQL. And then kind of we had a sibling team that created React. So I like to say that we were present at the creation of the full hipster stack. So our data tools are like live and reactive and beautiful. And I think you'll see it's like a kind of a new standard of tooling here. So as you execute this thing, you get a live log of everything that's going on. It's live and reactive. You can kind of get a sense of these computations. So for example, every single step that happens, it does a type check. And then as part of that type check, it also renders metadata for you in this structured format. And so this is all very nice. Let's see what else. Oh, so this is now like kind of our local development environment, right? So one thing I'm going to do is I'm going to set this so that one of the things our type system allows us to do is that as the DAG executes, it will actually persist all the intermediates that get generated along the way. And this unlocks a lot of power. So I'm going to execute this. And now let's imagine, oh, that's not what I wanted to do. Go here, whoa. Now let's imagine I injected an error here. Let's say, all right, I screwed something up. I am a bad programmer. Okay. Now I execute this thing. And now this is going to do an error, right? So I can click here, I can get a stack trace, figure out what's going on. But what's cool about this is that this is a really fast, trivial DAG, so it doesn't take much time to execute. Imagine this is like a 50-node DAG, and it was like a whole bunch of work, and you're just about to go home for the day, and then the 50th task fails. And you want to kill yourself because you have to fix one little bug and then re-execute the whole thing, which totally sucks, right? Here, instead, you can just re-execute this single step over and over again, and it uses the intermediates from the previous run in order to deal with that. So we run this thing by itself. We still have the same error. Go here. Re-execute this single step. Now it works again, right? So in a really complicated DAG scenario, you can see how useful this would be over and over. And this is actually how we actually get incremental computational semantics happening server side as well. Other fun things with this system, you can execute subdags, right? So you can actually go here and say, hey, I don't want to execute that read CSV command that you coded by hand, right? But now you have to provide the input. So now we start execution here. So you have to provide an input to this pandas data frame, right? And so what you can do is that pandas data frame actually not schedules, it publishes how it can kind of hydrate itself from disk. So you directly from the config here, you can say like, actually, I want to load from there. And so having this config system be able to drive loading data from wherever and like hydrating it into memory means that we can execute arbitrary slices of these DAGs, right? Which helps operationally, and it also increases their testability. Let's see here. So let's talk about testing. So one of the nice things about this contract that you see, where it says like, hey, this is a node, it has these inputs, it has these outputs, et cetera, et cetera, et cetera. What that says is that it is a contract that tells you what the state of the world needs to be before the execution proceeds for this thing to work. Meaning that here, what it says is like, hey, there needs to be a pandas data frame that's somewhere, right? And if that thing exists, my computation will work. Translate that to any other task management system that doesn't have this type of metadata system, you have no idea what the state of the world needs to be for that task to execute, right? If there's just a task called foo in the middle of, like, say, an Airflow DAG, you have no idea what the state of the world needs to be in order for foo to execute properly, right? Having this contract is enormously powerful. And what that allows you to do, to go back to the presentation here, where did that go? So now we move on to test. And I'm not going to dig into this that much, but we provide a bunch of nice kind of in-memory APIs. So you can just, within our runtime, execute a solid on its own, or execute a pipeline on its own, right? And what's nice about this is this plugs in, and we'll go into this in a second, the system kind of mocks up all the internal infrastructure needed to run this thing. So these runs have no dependencies on any external runs database or anything like that, right? But it's still executing the context of our runtime. So the point of this, not so you understand like this code sample, the point is that we have designed and published APIs that are specifically designed for you to run testing in your local environment, testing in your CI/CD pipeline, et cetera, et cetera, et cetera. So now let's talk about productionization. So you've written your pipeline, you have a DAG, you're thinking about your DAG from day one as you're developing your app, which is good, in my opinion. But now I want to deploy that. Okay, well, we actually come out of the box with kind of some automatic deployment to AWS. So if you run some command, right, you can go in and it'll spin up a node for you, security groups, key pairs, all that stuff. The mandate to the team was don't make people touch the AWS console, because who wants to interact with that thing? No one does, let's be honest. So just from a command line, you can spin up ephemeral infrastructure and run a Dagget node. And then all of a sudden, you're running that same exact web app, but it's up in the cloud. And you can execute on cloud infrastructure. Instead of your runs database, like in our local example, was just like poking at some local SQLite database, now it's pointing to an RDS instance, Postgres instance, right? Production grade. So you're using the exact same development environment. Well, you're using the exact same piece of software to do both local development as well as execute your jobs in the cloud. And this unification is actually really, really powerful. So now we want to be able to schedule these things, right? You write a pipeline, you've tested it to your satisfaction, you've deployed it. Now you want to schedule it. And so we come with a native scheduler, which is very simple, right? All it is a Python wrapper over cron. Turns out cron works. Cron works very well. It's worked well for 30, 40 years. And we have a way where you can say like, hey, here's this function which contains a Python data structure which represents your pipeline on a schedule. Why don't you invoke that and then run it with a certain configuration, right? We kind of stepped back and we thought about the requirements of a scheduler. It's like, we don't need to overcomplicate this. And so, with the scheduler, let's go over here, based on that code, right, you have like a scheduler, it's right there, right? And this is again like a live, I should have had this one on because, this is like a live updating UI. If I wait 1 minute for that next schedule to run, you'll see it magically appear here, which is fun. And you can search for all the schedules which came from a certain one, like all this stuff, right? So you can, you have out of the box like a very simple scheduler. But all of this is structured on APIs too. So if you have your own scheduler, it's very easy to invoke new runs based on that. So, between these tools that I've showed you, you can go all the way from local development, deployment, to scheduling, doing both local development and monitoring, all with the same tool set. It's actually quite powerful. So I want to dig into testability here, because I think it's an interesting lens to kind of explain a bunch of the principles of the system. So when you think of the status quo today in data systems, and you divide testing into, say, unit test, which is like you can run a test on your local machine without touching any externalized resources, to an integration test, which might be in a CI/CD pipeline, but you might have to spin up a Docker container or something, to a staging environment if you've done a lot of work, right, which is basically a replication of your production environment, maybe on some sample data, and then your full production environment. If you talk to most data systems today who build them, kind of the percentage of testing done at each stage looks like that. Like in reality, most testing, if it is even done at all, is done at production. And there's good reasons for this. And the primary reason for it is that testing these systems is really hard. They have very specific constraints that make them difficult to test. Namely, that you don't control your input data sets, right? So it takes a lot of work to simulate those. And two, most of your business logic is often hosted in computational runtimes that are impossible to mock locally, right? You cannot like mock Spark in process in Python. Doing that would be building an entire company unto itself. It's like not enough work. It's not enough, it's too much cost for the benefit you get. And so, I think testing in the data systems can get a bit of a bad name because testability people in software are very opinionated. And they're often very zealous. They start giving you speeches about mocks and stubs and how you're not doing anything right. I don't know if you've ever experienced this. This has been my experience frequently. And I don't think they really appreciate kind of what the problems are in the data domain that I was talking about. And so when it comes to testing, there's a couple principles. One is that things that can be caught by unit tests should be caught by unit tests, right? So I'm talking about things like parsing a configuration file, or figuring out in Python that you're calling a method that doesn't exist, or things of that nature, right? These are things that should be caught in unit tests. In the current day data systems, they're typically not, right? You don't really catch that stuff until you're in production. But there's an important corollary, which I just mentioned, which is like, don't attempt to catch things earlier in the process than you can, right? Like a data quality test, you have to run them in prod, because like that's where the only place where it really makes sense to run them, or you have to in order for it to make sense. You shouldn't try to unit test Spark in too much detail, because it's impossible to mock. So I think if you have this in mind, what you can frame the goal is not to like say that, oh, everything should be unit testing and everything should be caught in the CI/CD pipeline. It's not realistic. But what you can do is kind of shift the gravity so that it's earlier in the process. And that shift in the graph might not look like a big deal, but if you actually succeed in moving most of your testing to unit and integration testing time, that is like an order of magnitude improvement in developer experience. Because as the farther you push testing down the line, it becomes more costly in terms of the developer feedback loop to catch it. And I think this is like, the other thing I notice in these data systems is that frequently the code quality is at a lower bar, and there's like systematic degradation. It's not because the engineers who are interacting those systems are worse. You take the same engineer, you put him in one of these data systems, and the code quality isn't as good. It's because the act of doing like a refactoring task of something is way more risky, because you don't catch the error until you're later in the process. So it's important to try to front load this as much as possible. So Airflow does not address develop and test, right? Typically when you're using Airflow, right, you're just working in your own little universe in your job, and then very late in the development lifecycle, you plop that job into the Airflow DAG construction zone, and then you just kind of ship it off to production and hope and pray, right? That's typically the workflow. So really, Airflow only addresses the productionize and the schedule part. And therefore, it doesn't view the DAG really as a first-class programmatic concept, which I think is the problem here. So let's just dig into this, right? Airflow tasks are, well, it's a little confusing actually. The Airflow documentation hops between operator, task, and task instance. It's often kind of hard to know what they're actually talking about. But operators, when you create one, it actually creates a task. And so here, if you look, the task itself doesn't have any user-defined parameters, right? So like this load to HDFS instance right there, it's a function with no parameters effectively. And that task instance is bound to an environment. You'll notice that like local dir and HDFS dir are hard-coded to some temp directory, right? It's not parameterized. Whoop. And so it's bound to an environment, and that task creates a DAG. And because the tasks themselves aren't parameterized, the DAG is not parameterized, right? So these things have no parameters. And so you might be thinking, if you're an Airflow expert, like, well, there's all this other stuff. So yeah, there's no parameters, but you can kind of model data flow through XCOM, but it's really odd, right? Because Airflow's documentation says like, well, you should never share data between the tasks. First of all, it's a little wrong, because all you're doing is not expressing some dependency that exists, right? In order for there to be something's dependent on the other thing, something had to happen first, which means that this had to affect some sort of externalized state somewhere. It makes sense that it should pass data to the next task about what the hell it did, right? And so there's this feature called XCOM, but no one in Airflow really says they should do it. It says like, oh, this absolutely can't be avoided, don't use XCOM, right? They're basically saying don't use this feature. And in fact, the creator of XCOM kind of has sworn it off. So it's like, okay, we have this thing, but don't use it. And so in the end, what you have, again, is a DAG of parameterless functions. This is a common theme in Airflow land about like, don't use me. You know, we have this real construct for a composition called a subdag, but every Airflow practitioner I know says, don't use that thing. So there's been these stabs in Airflow for higher level programmatic constructs, but it's always kind of been a swing and a miss, to use an American colloquialism, and which is interesting. So another thing that I mentioned, which I'll go through quickly, is that Dagster has this pluggable system environment. So Airflow, for example, they store runs in a database, right? So typically you have to have a database running locally or server-side in order to encode that. Well, we have a much more pluggable system environment. We're in different contexts, the different subsystems, whether it's the run store, our logging system, or where we store our intermediates, kind of happen in different spots. And this has been very deliberate in order to make this system pluggable. I'm going to skip the pluggable user environments for a second. So all this testing stuff, the kind of theme is that we're not claiming this is automatic, right? But what we have done is we very deliberately built the system from first principles so that testing in a cohesive way is very possible. And it's going to be up to like the entire ecosystem of people to kind of build tools and help stuff out. But this is a very stable foundation with assumptions that allow for this testability. So stepping back for a second, what the core feature that allows the testability to happen is that we think a lot about parameterizing these computations. And yes, that helps testability a lot, but it's also like the core difference between it and other workflow engines. And it's going to be that property which enables it to be used for other use cases as well. So parameterization actually enables data science, right? It's really, really critical for data science workflows for these computations to be parameterized. Because in order to build a data science ML pipeline, you want to be able to run it 50 times with different parameters in order to, say, do hyperparameter search. You want to have it do that on the same instance of code in a verifiable way, so you have reproducibility and whatnot. So parameterization is incredibly, incredibly important here. Metadata. I'm actually going to skip to my demo here and talk more about this metadata stuff. So let's go to a more complicated DAG here. So this is a more real DAG, okay? This is a couple things that I want to point out here. So one is that there's tons of metadata that was very richly expressed here, right? There's inputs, there's outputs, there's user-defined descriptions, right? And each one of these is a function, right? And the function says that, hey, these inputs need to exist in order for my computation to proceed, and then it produces this output. And then you do dependencies based on that data flow, right? Well, because these are functions, right, what's one of the best things about functions? Well, functions compose. It's a very useful property of functions. So just as functions can call other functions, solids can call other solids. So if you go in here, so you click on this, there we go. That is actually a DAG of solids which exists within another solid, right? And this arbitrarily can nest. So if you go over these ones, this one goes down, and here's another reusable thing. And now here's this like reusable, this is like nested, and it actually makes it so you can reuse this thing all over the place. So like, for example, this one solid, which is cache a file from S3 in some local cache, that is used like 8 times throughout this pipeline in different parts of the stack, right? This is like a level of reusability and composability which does not exist in the existing systems. So, with this metadata, if you compare this to an Airflow DAG, right, this is what the Airflow DAG looks like in the UI, right? All it is circles with a label, and then arrows between them, right? Tasks, and then the execution order of those tasks. That's it. That's all the metadata. That's all the metadata that the user gets just to view it and understand it. But more importantly, that's all the metadata that the system gets in order to actually do useful things. By contrast, right, I just showed you this. This is a much richer system in terms of expressivity, right? You can understand what's going on better, presumably. You can compose things. You understand the data flow. Also, what the configuration required is to need to execute this thing. And, in fact, click here, this, and I'll go into how this works, this DAG up to the left here, this is actually compiling and actually programmatically creating that Airflow DAG. And I'll go into how that works. But it's actually a layer of abstraction. It can be used as a layer of abstraction above Airflow. So the other thing that I wanted to show, see, we have 4 minutes left, is how this can be used as kind of a multidisciplinary pipeline. So the example I showed you kind of before was just basic Python code, right? But here is an example pipeline where the first thing is actually executing SQL in some database. That kicks off another SQL job. This one actually kicks off a Jupyter notebook. And if you heard the first talk, Michelle's talk, I don't know if Michelle's here, but this actually is invoking a papermill notebook as a function, right? And so what this represents is a pipeline that gets integrated, right, and is using solids crafted by different participants in the data application. So if you think about this, right, here's kind of like a representation of a data application that involves multiple different parties here. And they represent different constituencies, right? So you might have the data scientist creating the notebook that ends up getting parameterized. You might have the data engineer building the PySpark job or the Scala Spark job. And each one of those things can be represented as a solid, right, as you saw in the previous UI. And so the system, right, at the end what Dagster is, or one of the things it is it's an API by which you can query these computations for their metadata. So you have an abstract computational graph, which is represented in that UI that I showed you, accessible behind an API. Each one of those solids can be implemented in arbitrary processing tools. Again, from the standpoint of the system, the implementation of a solid is a totally black box function. So this is any storage, any language, any runtime. You have our Dagster native tools. So that's that log viewer I showed you, the graph viewer, the live log viewer, the simple scheduler, all that stuff. But we also integrate with existing ops and infrastructure, right? This is just a Python library, and it's just a software abstraction, which means you can deploy it on arbitrary computation, right? So you could execute this on Kubernetes. We have an out-of-the-box Dask integration, if you want to use that for your orchestration cluster. And so this makes it, the fact that it's a pure software platform makes it super powerful in being able to execute on arbitrary infrastructure, right? And so like I said before, all the integrations kind of underneath the abstraction can interact with libraries that would be written by any of these constituencies here. They're all operating on the same logical DAG. They all collaborate to build this data application, which is the abstract graph of computations. That's all accessible behind an API. And that's how we build our local development tools here. But what's interesting is that, like I showed before, we also have the ability, for example, to use the API to actually say, hey, give me this DAG, here's this configuration, programmatically create me the Airflow DAG, which corresponds to that. Which means that if you have an existing Airflow cluster and you want to experiment with the software abstraction without totally thrashing your infrastructure, maybe you don't even want to talk to the people who maintain your Airflow cluster because they fear all change, right? You can actually integrate this at the software layer without disrupting any of that. So, just to summarize, what Dagster is this system that supports the full data application lifecycle, meaning from develop to test to deploy, and then scheduling and execution, right? You kind of like stay in the same mental mode through all those phases of development. Those properties make it amenable for both data science and data engineering. And we really do think that these tools that we built on top of it really set a new standard for kind of the developer experience and the user experience on top of these beautiful web UI tools. And with that, I will close it out. Thank you for listening.
Thank you so much, Nicholas. Okay, so we're going to open it up to the Q&A. If you've got any more questions, hand them in. So, how stable or mature is the framework at this stage?
There are no bugs, and it is perfect, obviously. No. I mean, so this is definitely like on the early side of a framework. And, so there's advantages and disadvantages of that. One, it's not as battle tested, right, as something like that's been around for 10 years. But it's under super active development by what we hope are reasonably competent engineers who respond extraordinarily quickly to both feature and bug requests. So, if you adopt this, you definitely have to roll with the punches a bit and talk with us on Slack. But, we're confident that it can be used in production pretty effectively today.
And how is the metadata and data from the DAG pipeline execution persisted and or reused?
That's a great question. So that was one of the slides I skipped, actually. But metadata is a very broad term. The metadata I was focused on during most of the presentation was metadata about the computations itself, meaning that you can query it and ask it for its DAG structure, right, and the types and all that kind of stuff. But there's also this metadata that each of these solids emits facts about what's happening. So instead of just unstructured logging, it will say, hey, I just passed this data quality test. I just created this materialization that will outlive the scope of the computation. Right now, the only way we persist that is in this structured event log, but we hope to work with our users and to build up the stack such that that can easily be used to persist kind of an artifact store or a system of record for metadata. So that's a great question, and that's where we're going with the system.
Right. So does Dagster only have a time-based scheduler or event-based as well? For example, all upstream pipelines are finished.
That's a fantastic question. Right now, natively, it's only a time-based scheduler. As I said, these invoke. We have spoiler alert. We have a GraphQL API over all this, and what you can do is if you have some event-based trigger, you can just invoke that API to enqueue a scheduled execution. So, if you want to use it to watch an S3 bucket using CloudWatch or whatever, you can kick off a pipeline job based on that.
Okay. How far is Dagster from 1.0?
Oh, these are one of these mystical questions about when to call something 1.0. I mean, pandas, for example, still isn't 1.0. And it's probably responsible for the entire popularity of Python in the data ecosystem in general. So it's a relatively arbitrary term. I get asked this all the time, so I probably should come up with some sort of coherent shtick about when we'll call it 1.0. But it is relatively arbitrary.
Okay. How do you version control your data?
That's a very good question. We are currently not opinionated on that, so we don't have some sort of Git-esque API for data. So that is currently up to users to roll their own stuff.
Okay. How do you deal with states of pipelines, for example, knowing which rows are new since the last run to manage change data?
I have to think about that. I mean, knowing which rows have changed from a pipeline, we consider part of the business logic of the pipeline itself. I think it's very difficult to have a super opinionated viewpoint on that without having much more context about what the computation is doing. So I'm going to punt that and say, like, right now that's not a concern of our system. We would consider it part of the business logic of your pipeline.
Does the DAG serialize data between all solids? What if I want my Spark data frames to be optimized by Catalyst across nodes?
Ooh, that's a great question. So as far as I know, does Dagster serialize the data between solids? The answer is yes. That's part of its capability. So you can express things in terms of inputs and outputs or data frames, and then the system will be responsible for serializing the contents of those things so you can pass them from node to node. Now, Catalyst is an internal implementation detail of the Spark engine. So it's their internal in-memory format that's used within the context of the Spark cluster. So that's really only relevant within the context of one Spark job, which would be contained within a single solid. Now, I think the question you maybe wanted to ask is, can we use a system called Arrow, which is an open standard for in-memory data frames? And I think that would be a really interesting project to have, to be able to use. What I would probably propose is there's this in-memory object store called Plasma, which is a project called Ray, and you can persist Arrow within that, and you could use that as the intermediate store between the solids. But whoever asked that question should come talk to me, because that was very good, and maybe you can come work for us.
And on that note, Nick is going to be in the Prezi booth, which is in the sponsors hall, just sort of behind the info booth. He'll be there for the next 20 hours if you want to talk to him further.
20 hours?
Oh,
wow.
Did I say that out loud?
That's a marathon.
I definitely meant 20 minutes. My bad. So thank you so much, Nick, on behalf of the conference.
Oh.
Please.